All right, so after you guys get a good jump on it, I like to go ahead and jump in, and now you have some context to what we're dealing with together, okay? So obviously today is about measurement in some way or form, and we're going to be looking at instruments, specifically in this case rulers. Later on we'll be looking at graduated cylinders, burettes, anything that we can measure with in chemistry, and really determine like how accurate is it, how precise is it a good tool, is it a really crappy tool? So like look at this ruler right here, would you consider it really good or really crappy? Really crappy, like it has virtually no graduations on it, right? So what can you be certain of? Anybody, what can you absolutely be certain of? Yeah.
That it's summed up to 3 centimeters.
You're like, well, this person's, whatever this little bar is here, it looks like it's 3, but you're not certain of it because there's no number there, right? What are you absolutely certain of? Yeah. It's between 0 and 10, right? Great job. That's all we really know because our ruler is very limiting in our accuracy, okay? So if 6 students were to measure this, we might measure it differently. So you said 3 centimeters. Give me something else. Anybody else? Can I get a 3.5? Yeah? 4? Yeah? 2.5? So it's going to be varying. It's going to vary based on who's looking at it. It's got some bias behind it because there is no help, meaning no graduation. So it's not very helpful. Looking at ruler B here, it's a little bit better. What can we be absolutely certain of, Brandon? Right, so now we're certain it's between 3 and 4. We know it's at least 3 centimeters long. A little bit more, but we're not quite sure of, like, you know, what the decimal is. So this is where we get to estimate. And so the estimated digit is something that's going to vary for everybody, but it's considered a significant digit because it has to be recorded, because somebody has to make the decision of, you know, what is it past 3? Is it 3.1? Is it 3.2? So we have to give a little bit more of an indication of what we know here. So it's a better ruler, distances that we know. Were the students able to agree on a single value? The first value? Yes. The second value? No. And where's my clicker? There it is. They also, look at Emily. She's like, heck yeah, I know it's 0.25. And Dion over here says it's 0.20. So they're actually estimating another digit, but that's not really valid because they don't even know for sure it's 0.2, much less is 0.25 or 0.20. These people up here know what's going on. They're like, I can only estimate a little bit. I can't keep going and say it's 3.22222222000 because that means that they're incredibly accurate because they have a lot of digits to indicate that. Okay, so what feature made it possible? There were more graduations. All right. So one of the key points, this little key thing means it's a key point, right? Okay. There's always uncertainty in our measurements. The last digit is the one that's the most uncertain digit because it has that estimated bias behind it. Okay, so there's various causes based on people's bias. Looking at ruler 3, C, you can see it's very, very good, right? So who here, based on kind of what I've been talking to you about, who here do you think is most accurate in terms of their number of sig figs they should be recording in their measurement? Looking here too. So like here, let's just give some estimates here. Matt, tell me what your estimate is of this guy.
3.2.
Okay, this Matt. This Matt? Matt, did you say 3.2?
He said 3.2.
Okay, I was like being really close. Okay, so 3.2. But there's actually all these little tiny numbers afterwards, right? I'm sorry, 3.2 is actually what it is because it's 3.2, that little tiny dash right there. But 3.2 what? So the estimate part is what you get to, you have some roll in, okay? So 3.2 what?
3.21.
3.21, right? So all these people over here, 3.21, 2022, those people know what's going on because they know they can estimate that last digit, even though it's different. It's still, you're still supposed to do that. This person, Mark, he just didn't get the point here. You have to estimate past what you know. And Emily and this girl, they still think that they're Superman and they're estimating farther than they should be. Okay, so this basically, I don't want you to lie about your measurements. You want to be able to record what you definitely know. All right, I'm going to scooch down to this one here. I don't think many people, well, some of us dig it here, but not all of us did. Okay, so number, are we on 9? Number 9, the measurements taken in Model 1 through 3 have been combined. The measurements that follow the rules of measurements agreed upon by scientists are the valid measurements column. Those that do not follow the rules are in the invalid measurements column. For each of the valid measurements, draw a square or a circle, and you guys don't have to draw it. You can just write it out to the side and square it. Draw a square around the certain digits and a circle around the estimated digits. So based on the valid and then the invalid, up here, which are the ones that are valid, or which ones are the ones that are certain? How about in this column? The 3 and the 2, correct? over here, the 2 to 3, the 3, those are all certain. The ones right after it, what are those called? So the 2, oops, can I write on this? Yes. Oops, I'm supposed to square those. These are all certain. The ones right behind it, those are circled, those are the estimated ones. But that like last 0 on the second one, 3.00, that last 0 shouldn't even be there because it's not valid to assume you know that much. Nor is this 3. So those should not be there. So the second one right after the digit right after the decimal is an estimated digit. So you can see down here, let's go ahead and jump to ruler C here. Which ones are certain in this column over here? Which ones are certain? 3.2 are certain, right? So I'm going to kind of square those right there because you can see the 3 and you can see the 2, but you don't know right after it what it should be. So then the estimated ones here are 1 and 0. And the 5s down here for these last 2 measurements are invalid because we're not able to estimate that far. Yeah?
On the first one, how do you know the 3 and the 2 are certain if you can't see the lines?
You're right, actually. So this one, there is an estimated, I should have been looking at this one. I was jumping the gun. This one right here, the certainty is the 0 and the 10, so there's not actually a 3 there. So these should be the certain ones, and 2 and 2 here should be the estimated ones. The last 2 are the invalid ones because they're not supposed to be, you cannot estimate past the first digit. So this one, not bad, none of those. These are all estimated. That's why I was trying to circle these. Here, here, oops, here, and here. These are estimated because there is no certainty of the 3. Good point. Okay. So I'm running through this a little bit because I think you guys have had some time to marinate with all the snow. With this information, what are your general rules here? If you have a really good ruler, you're going to have a lot more digits. If you have a really crappy ruler or any kind of instrument like a beaker or a flask, you're going to have very small number of significant digits just because your instrument's really limiting you in your accuracy. Does that kind of make sense? Okay. So let's scratch the rest of this one out. Let's jump into notes. There is a half sheet in your folder that says lecture notes, and I will have some information on there for you so you don't have to write it down. I'll also have you guys reference your reading guide on some of the information because it's a repeat, and it'll help you kind of pull together what you previously looked at and what you're doing now. So we're taking notes for a little while. We'll do some practice problems built into the notes. If you have a calculator, I'll pull out your calculator. If you don't have a calculator, I'll come around now. Raise your hand if you don't have a calculator anymore. Okay, so kind of how I do notes is, I have a second line if you guys ever want to print it, you totally can. I usually talk a lot. It's just who I am. I own it. So I'll have you guys write down what you want to here, but a lot of times I might expand upon it and I'll write some additional notes on the board. But some of this, if you feel like you're like, duh, I know this, write down minimal. If you're like, oh my gosh, I don't have any idea, take a picture or write it down and thoroughly. This first part is just some information about background information about how do we know what we know today. Well, we've all heard of alchemists, right? So if you can't explain something, you're like, it's alchemy. And that's just a kind of a cop-out. Because if you can't explain something, you should dig into it. You should trial run things and see if you can figure out any background, real science behind the concept of the phenomena. Well, we didn't know that back in the day. We were like, everything's alchemy if we can't explain it. So, but the alchemists, because they wanted to explain things, they kind of developed skills, tools that we still use today to start prying into the nature of science and like how do things work. So they're who we think for the techniques and tools that we use today. So that's just an identification of a group of people, the alchemists. And they actually led us to kind of stray away from magic and mystery to logic and reasoning. And that's why science is supposed to have such a logical basis, so we can explain things in a way that makes sense and not just because, right? There is a reason behind everything. So they're the ones who kind of made us go down the path of logic and reason versus mystery and magic. One specific guy who helped determine some interesting things about science and chemistry was Antoine Lavoisier. Okay, so he's a pretty old guy. Most of the scientists we see are old white men. We soon will discover that there are other people in science than old white men with little lab jackets on and a pen pocket. One of his biggest discoveries was combustion. What does it mean to combust? I see jazz hands. Okay, yeah.
Put yourself on fire.
Okay, but what's actually catching it on fire? It's the presence of a gas. Oxygen. So it's not only just the explosion part, that's the after effect, that's the wow factor. It's the actual reaction with oxygen that we call a combustion reaction. So reaction with oxygen, O2 is oxygen, that's going to be actually what the definition of combustion is related to. One combustion reaction you're probably very aware of is the one that happens in your body with glucose. Cellular respiration? Glucose, give me the formula. Shout it out. Actually, this one, we're gonna do aerobic respiration. Okay, so glucose plus oxygen, it makes a gas that we breathe out, carbon dioxide, and a little water. I'm not going to balance it right now. I'm just going to show you the products. Okay, the carbon dioxide we do breathe out, the water we use for other places and metabolic processes in our body, and it also makes some ATP, but that's like biological energy. We actually are more interested in like the fiery output, which is the chemical energy. Okay, so whenever combustion occurs, it always reacts with oxygen, and it always with this hydrocarbon here, it always makes carbon dioxide and water. So Antoine Lavoisier is like, hey, it's always making the same thing. Is there a way I can kind of analyze the products, meaning analyze how much of this is present in relation to how much this is present? And he did. He figured out you can analyze that, and you can actually figure out what the heck the fuel was. You could figure out what it was. So in our bodies, we're using glucose, but there's many other ways to combust things. Anything CX, so the carbons can change, the oxygens and the hydrogens can change. So he did this thing called combustion analysis because I kind of itemized what was produced to figure out more about what was burned. So that was one of the very first things. We actually learned how fire worked with that. And through that process, he was like, hey, if I've got, let's say, 6 carbons here, I had to have had 6 carbons there. And if I have, what is 6 here? So 6 times 2, there's 12 hydrogens here, then I had to have 12 hydrogens there. And so he kind of saw the relationship of what we have here was what we had here as well, but they're all mixed up. And so that is the law of conservation of matter. And matter has mass. And that was the second law, or that was the law that he actually determined. So we credit him with the law of conservation of mass through experimentation with combustion. Thumbs up? Good? Okay, so I told you I like to talk a lot, but there's more to the story than just black and white here. All right, so now we're going to get into metric stuff. Who recognizes these guys? They're all in your reading guide, right? If you did a very thorough job in your reading guide, you do not need to write all this down again. Put a star in your reading guide, say, notes or something like that, because that's what I'm trying to reward you so that you don't have to write everything down. So two distinct things we need to learn about today. Measurements are not negative, right? Measurements have a number with a unit. These are markers. And that unit comes in many varieties. Units can be meters, kilograms, seconds, amps or amperes, kelvins, moles, candelas, or liters. The 3 that we'll utilize a lot are meters, kilograms, and liters. Those are kind of our 3 basic measurements that we're pretty familiar with, and we have tools to use that will create these measurements or these units for us. So we'll use, for example, we'll use a scale, an analytical scale or a triple beam balance to get kilograms, grams, which is a unit of mass. That's going to be kind of like its weight almost. We have rulers or meter sticks to give us the unit of meter. So we have things that measure length. And then what do we have to measure some sort of volume unit? What tool do we have? Graduated cylinder, right. So the graduated cylinder is our go-to for most of our things involving liquid volume. So those are some of the instruments we'll use to get these units. These are the symbols for them. So meter, kilogram, or gram. We can use gram as well. It's not specifically an SI unit or it's the unit of measurement that the entire world agrees upon. They like kilogram, but a lot of times we don't measure kilograms of stuff. We measure small amounts of things like grams of things. And then liter or milliliter will be our go-to unit for anything involving liquid measurement or solid measurements like a rectangular prism or something. So we have to use these units. So you'll notice what's not up there that we commonly use in America. Inches, feet, Celsius even is not up there, but it's related to Kelvin. Fahrenheit, there's all these units we don't know. We use in America because we're special for some reason. The rest of the world decides that they will keep a consistent unit of measurement so that if I'm reading a publication from England, then I can understand what they're talking about. Like I can understand that they used, a specific mass of iron to react with oxygen and they got this versus me trying to convert, to a unit that I use that nobody else uses. Because I could totally make up my own unit and I would call it something with MLO. You have, whatever you do that's special, you have to name it after yourself so everybody knows, okay? So, I don't know if you guys, I don't have my good periodic table up, but the last four, umphium and topium and neptunium and all those things down there, they were just discovered 2 weeks ago? 3 weeks ago? Not discovered. They were claimed to be reproducible, so that they're going to now actually name them. Okay, anyway. So, along with these units, we can actually perform calculations with them. And you're totally expecting that, right? We can perform calculations with many things. But the things that we do calculations with, we actually name them. We call them derived units. And derived simply means to perform a calculation with them. So derived just means it has a calculation kind of built into it. And density is one that we've all heard of density. You're familiar with density. You're familiar with the concept that it is a calculation of division by taking mass divided by volume. And a common unit for mass would be grams, and a common unit for volume would be milliliters or centimeters cubed. Those are going to be our two that we refer to most often. Another one that you're familiar with from geometry is area. Area is not a unit itself, it's a derived unit, and it's derived from length or side. So meter squared or side squared would be how that's related to geometry. So it's just a special name for a type of unit that requires calculations. Yes? What's the definition? It just means a unit that requires a built-in calculation. So you must complete a calculation to kind of get it. So like if you look up here, area is not one of my given units, but I know we can find area because everybody knows area is side squared or length times width, something like that. So it requires a calculation to attain it. Okay. Another one that you need to know, and you've written down in your reading that I believe, is the process of finding Kelvin from Celsius. So you just take your Celsius temperature, add it to 273, and you get the unit, or the temperature in units of Kelvin. And there are some temperatures that you need to be aware of, and they're here, so you want to write these down. So we're not probably going to math class, but we can make it. So just for kicks and giggles, Can you guys tell me what the room temperature is in Kelvin? If you need a calculator, you do have one right in front of you. So room temperature in Celsius is 225, 298, right? So you're just adding 273 to this, and so it's 298 Kelvin. And it doesn't say degree Kelvin, it's just Kelvin. Water, 273. Boiling would be 373 Kelvin, and then so forth. So it's not hard to calculate Kelvin. It's just something you have to be aware of. And if you ever need body temperature or room temperature, I would tell you that a lot of times in problems will say, this gas is at room temperature, and doesn't tell you the temperature. So that's one I think you'll become aware of as time goes along. And water, boiling, freezing, we went over last week, so that's not new to you. All right, we know that now we're going to only talk in Celsius and Kelvin, no more Fahrenheit. All right, so metric prefixes. Do you recognize these from biology and like lower grades? Yes? Okay. Those are ones that we're going to be referencing a lot with the intro unit because there's things that you're familiar with. So I'm going to ask you guys to convert between kilometers and millimeters or centimeters and decimeters. And we're going to convert not by just swooping the decimal. We're going to start to kind of dive into dimensional analysis, which is just chemistry math, which uses conversion factors. So I'm going to start it off with really easy things that you're well aware of. But we're going to move eventually to things like moles. Like, what's a mole? It's a unit in chemistry. So that's why I want you to be aware of your prefixes now so that later on you're good with the baby practice, and we'll get into big boy practice then. So these are your main prefixes in the metric system. And they're all based off 10. So these are each 10 or 1 decimal apart. So they're times 10 of one another. And there's an easy, cheesy way to remember them. You guys know what happened to King Henry? He what? Died by drinking of chocolate milk, okay? So, King Henry died by drinking chocolate milk is a really easy mnemonic way to remember this, the metric system line. But there's a little bit more than just that. We're going to start talking about really small things, which are like nanometers, picometers, and then further than that too. But I'll tell you the rest of them in just a second. So, what I would recommend at least you write down from this slide is just the letters that represent King Henry, blah, blah, blah. So King Henry died by drinking chocolate milk. You'll notice I went from capital to lowercase to indicate that this right here, which is base, is our kind of breaking point of being above 10 or below 10. Base, though, is generally going to be represented simply by meters, liters, or grams. So there's no prefix in the front of it. There's no millimeter, it's just meter. There's no milliliter, it's just liter. And then these others are going to be above and below. Well, there's a couple more that you need to be aware of. I'll scroll up here. So in front of kilo, there's actually something called mega. Okay, so it's 2 decimals away. So I actually put like these little dots here to represent it's 2 decimals away. So mega is actually 1,000 times greater than kilo. It's 1 with 2 zeros. So it's like 1, 2, 3 decimals away. So it's 1,000 times greater because there's 3 zeros that are placeholders. So that's why it's on that side of on kilo. On the other side, we have other prefixes that most of us may have heard of. Nano, but there's not much else. Okay, so there's milli. So this is deci, centi, milli, ... There's micro here, and micro has this funny U shape. It's like a U with a big tail in the front. So that's micro, like a microscope. You can get down to microns if it's a really good microscope. And then there's 2 more zeros that are placeholders. And then you get some nano. We've probably heard of nanometers, maybe. Nanoscale science. And then there's 2 more placeholders, and there's P for pico. P-I-C-O, pico. And we won't use that one as often, but we will use micro and nano. So that's why I'm extending our prefix number line a little bit here. Thumbs up when you got this one. And you recognize that these decimal points here are placeholders, they're zeros. Okay, so for example, nano is 9 spaces away from the center. So if you look at it, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. I remember that one because 9 or 10 to the 9th power is representing the nano unit. It's very, 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 very tiny. Or 10 to the negative 9th if you're going to be on the smaller side. But it's like a billion times smaller than the base. Okay, so we're going to be using that as we go, but let's just kind of kill some of the intro stuff first, okay? Scientific notation. Thumbs up if you used it. And you're good with it. Prove it to me by changing this to scientific notation. I'll help you count if you can't see it. It should be 24 numbers across. 24 numbers all the way across. So we're taking this humongous number and chase, it's 24 numbers across, all the way across. What's the very first thing you're going to start by writing? 6.02, right? Because the very first, so scientific notation indicates that our first number, our integer, has to be between 0 and 10. So this 602 is not going to work. 60 isn't going to work. So it's going to be 6, but you can't lose this number because that's probably an important number to record this value, right? So 6.2 is our first number times 10 to some exponent that allows for our decimal to get all the way back here, right? So if I'm putting a decimal here, and I told you it was 24 numbers across, what's my multiplier, or what's my exponent? 23, right? Because I need to count 1, 2, 3, 4, 20, 1, 2, 3 to get back to where our decimal is supposed to be located, indicative of our coefficient that we've chosen. So this right here is actually an important number in chemistry. It's called Avogadro's number. Avogadro's number, 6.02 times 10 to the 23rd. We'll start to recognize that one later in life here. But scientific notation is simply a tool for us because we're lazy and nobody has enough time to write out that many zeros. So we choose to write in scientific notation really, really, really large numbers and really, really small numbers in an easier method. It just helps us kind of expedite our mathematical processes. Okay, so this our next one here, so you'll notice a number smaller than 1. How would I note that in my exponent? Right, by putting a negative. So what would you guys be writing for the scientific notation? 3.880983. I'm actually writing all of these because these are significant digits. We're going to get to that in just a second. -3, right? Because if I put the decimal there and it's 3 away from where it was, 1, 2, 3 means I have to add an exponent of -3 to get it back to where it once was, to indicate that it's a very small number. This one right here, number 4, this information is the negative part of it is just going to be held constant. We're not going to change the fact that it's a negative number. So I'll put negative what? 895 times 10 to the negative, let's see here, 1, 2, 3, 4, 5, 6. So -6 to represent our difference here. Are these measurements? No, why? They're naked. They don't have any units, right? So we're going to start to use them as more, in chemistry terms, with units here soon. All right. For these, you can change the decimal or exponent or scientific notation back to exponential. Yes. Okay. Okay. So, does everybody have a piece of paper they can sacrifice for the sake of learning? The answer is yes. Yes. If you don't, you just watch. All right. So I saw we had some athletes. And I'm not sure, I believe your skill level, some people said like you're being drafted by the NBA, NFL, I don't know about that, but you can prove it, okay? So follow your piece of paper. And you're on that side of the room. We're basically, I want to see how accurate you are. And if you're accurate, then, you know, kudos to you. But go on that side of the room. Get the basket. Go. No, like swoosh. Let's go, swoosh. Oh. Okay, air ball, air ball. Oh, what? Okay, this other room. Keep going.
Nope.
Oh, yes. 2 for 30? Jeez, okay. So, there's a lot right here. There's a couple around the basket. There are 2 in, and there's a lot back here. Okay, so, which of these was the accurate shot? The two that were the true value. What we wanted was swoosh, right? Swoosh is now a number. We wanted that, right? But we had a lot of repeated measurements right here. Were they accurate? Heck no. Like, that's accurate, this is not. But what would you consider them? Very precise. Like, they can totally miss that basket over and over and over again. They repeated that I missed the basket trial. Like 7 times up here, right? They're very, very precise, whoever did this, right? And the people back here, they were also very precise. There's like 6 back here. But were they accurate? No. So being accurate is good, right? Being precise is also good, but it's a different kind of good. Being precise means that you can repeat your same measurement over and over and over again. That doesn't mean the measurement is true, or doesn't mean that the measurement is right. No. Accurate means it's right. Precise just means I can do that over and over. It's about the repetitiveness of it. But being accurate and precise means that you're going to have, like, all net. Yeah, all net. No basket. No backward net. It means that you're going to be very precise in your shot, and you're very accurate because it's going to just simply get the correct answer or the correct data for you're looking for. So that's the difference between accuracy and precision, okay? So I'm hoping that demonstration helped you a little bit. This is the most basic definition I can give you. I have another little blurb on the next page that will kind of explain a bit more. Write down what you need to know. So if you had to write down one word, you'd say accurate is true. Somehow the true value you're looking for. And precise just means repeated. How close the measurements are over and over and over and over again. And usually we're not going to be 100% accurate. Like, let's be real. We're amateurs at this. I barely get paid for this. You know, amateurs means you just don't get paid, right? I'm a professional chemist, so I get paid to do chemistry. But I'm always going to have error. You're always going to have error. And sometimes we have to denote how much error. If you just say I got it wrong, I want to know how wrong or how far off you were. And so this is our percent error calculation, which you did write down in your reading guide. If you'd like to write it in a slightly different manner, here you go. Usually, you'll notice that it's just the absolute value between your accepted value and experimental value, or the true value and value you got. So I usually just go alphabetical order, A minus E over accepted times 100. So A minus E over A. So difference in your actual and your experimental over the actuals. You're just comparing it to what it should be. So you're basically getting error over the actual value times 100, and you'll get your percent error. Yeah.
Experimented minus
It doesn't matter because I'm going to do absolute value. It's always going to be positive. So that's why I just like to write down my short, easy way, because I just know, like, think of the American Eagle or something, A minus E over A. And it's helpful because it's absolute value. It doesn't matter which way you subtract. So using your grand knowledge of room temperature, can we calculate the percent error in this experiment? You measure room temperature to be 28 degrees Celsius. What's the percent error? So write on your paper how you would set this up. All right, so would you guys write first? Yeah, go for it. Okay, so 25 minus 28, and it doesn't matter because either way it is going to be absolute value, so it's going to have to be a positive number, over what? Everybody? 25, which is our actual room temperature value. So this one you could have put degree C everywhere, but the degree C's, whenever you divide, they are going to cancel, okay? So this is 3 over 25, right? What's 3 over 25? Calculator, you got my math?
12.
So 0.12, is that just 0.12? Okay, so that's 0.12, but we also have to multiply by 100. I'm actually going to write it up, so it looks like I'm doing it in multiple steps. You can just do it in one step. So that's going to give us 0.12 times 100 will give us 12%. 12% error. That's pretty good. Like, if you're below 15-ish% error, that means you did a great job. If you have like 95% error, you might not, well, you know, don't quit your day job because you can't measure temperature very well. So this is just a way to measure how off we are from our true measurement. Okay, do not write all this down. Read this. The green part is basically what I was indicating to you for the difference between precision and accuracy. I think this is the best explanation, and I'll let you guys read it. Take a picture, whatever you want to do. Thumbs up when you're good here. Okay, like smile or something. Gosh. Okay. Let's go to sig figs now. This is the part. Go through this in your notes. Okay, not quite. I didn't put this part in your notes, but I think in 2 slides I did put on your notes. I just broke down a specific method you'll be using. Okay, so in measurement, we know there's always that estimated digit. We know there's always some true values that we definitely know, and then we always know there's error. Like everybody inherently has error because we're humans. But the things that we call sig figs or significant figures or significant digits, they're all doing the same thing. It's just the values that we know plus the additional estimated digit. That's it. And so we're just going to be counting them. And the reason we count them is because it determines the accuracy of that measurement. And so it's nice to know how accurate somebody's measurement is versus somebody else's. And sometimes it's going to limit our ability to really express our value in a truthful manner. So we're going to be talking about how to actually count the significant figures. So which of these is going to give us a more accurate measurement of this round rectangle? The second one. Why? Yeah. Okay, so this one's going to be more accurate because more graduations. But what does that also mean? This tool allows us to record more digits, yes, because there's an extra line here, so we can record. I know it's not much, but we can record one more digit, which means we have more accuracy. More graduations, which means that you record more significant figures, and that is a valuable tool to have because the more sig figs we have, the better our accuracy. Okay, so let's start counting then, and let's see if we can put this into perspective. This is the slide that I did on the intro part of your notes, and then there's some work problems that we're going to be working together afterwards, so make sure you have that out in front of you. Okay, so how do you count a significant figure? I'm going to do this with an example. So I'm going to start with the Pacific method. So 3.00200 meters. All right. So whatever this is, that's my number. That's my measurement. So the way you count significant figures is if you first look for the decimal. There is a decimal. So we say it's present. If the decimal is present, you start from the Pacific. And the Pacific is on this side, right? Okay. So when you start from the Pacific, you start counting digits, the first non-zero digit. Well, that's a 3 here, right? And once you start counting, you don't stop, like Pringles. Once you open it, or once you pop, you don't stop. So you start here, you count 1, 2, 3, 4, 5, 6. There are 6 sig figs in this number. If the decimal is present, I start at Pacific, and once I start counting, I don't stop. Okay? So what if instead I said, that's my number, measurement, okay? Do you see a decimal present? No, no decimal is present. So I'm not allowed to start at the Pacific, because Pacific goes with the decimal that is present. I now have to start at the Atlantic, because the decimal is absent. So Atlantic's over here. I'm going to count that side, right? So I have to start counting digits at the first non-zero digit. When do I start? Now, at the 2. So I skipped over the 2 zeros. They're just placeholders to indicate the scale of this number. It's a very big number. So skip. The very first number I start counting is the 2. And once I start, I don't stop. 1, 2, 3, 4. There are 4 sig figs in this number, which is more accurate. First one or second one? The first one, because it has more sig figs, meaning my piece of equipment was amazing. I had lots of graduations on it. The second one, not so great. Yeah, it's a big number. It doesn't tell me anything about its accuracy. It's about the decimal places or the number of sig figs that actually help with that. So that's called the Atlantic Pacific method. So let's actually try some of these. This one is on your paper, okay? This is on your paper? This is, okay. So I basically want you to chant with me here. Present or absent at Pacific, Atlantic, and we'll move forward. So first one, decimal's present, so where do I start? Pacific, and once I start counting, am I good to start? Yep. How many do I have? 3 sig figs. Okay. Present, absent? Present. Start from the Pacific. Do I start counting? Yes. Don't stop. What do I have? 4 sig figs. All right, let's go down to E. Present, absent? Absent. So where do I start? Atlantic, right? Starting on the Atlantic side. I'm on E, which is this one right here, okay? When do I start counting? At the what number? At the 2. So I'm coming from the Atlantic. I'm skipping the zeros because they're just placeholders. I start counting at the 2 and the 1. That represents 2 sig figs. Okay? And then let's do one more. Let's do H. Is the decimal present or absent? Present. So where do I start? From the Pacific. Okay. So when do I start counting? When? What number do I start counting at? At the 2. That's it. I have to skip over these because these zeros, the leading zeros are placeholders to indicate this is a very small number. The ending zeros, like in this one up here, those ending zeros are just placeholders to say this is a very big number. Those zeros don't really tell us a lot about the measurement itself, just that it's big or small, not the accuracy of it. So that's why this 2 is the only one that's actually helpful in telling us the accuracy of this measurement. So there's 1 sig fig there. Last one. Present, absent. Present, when do I start? Pacific, and when do I start counting? Now, so at the 4, and I keep going, so there's 4 sig figs. All right, you guys do the rest of those right there on the very first section with your partner, and I'll put the answers on the board for you. Okay, and right up here are those 3 that I didn't do on the lower section. So D, 6 sig figs, thumbs up. Yeah. Did you get that? Thank you. Okay, some emotion, people. F, 3, and G, 2. We okay with this? Counting. Right. We're going to be using the counting scheme much more with calculations now. Okay? So this, no, actually, let me do rounding and then I'll go to calculations. This rounding part is not something that most people like a lot because sometimes it's confusing. But if you get it, you actually know sig figs better than you probably ever will. Okay? So when I have this huge number here, 50,600.06575, that's a very large number. But let's say I need you to round it to 1 sig fig. You can't change the number. Like, you can't change the value. It's still going to be 50,000 something. So I can't record all of those digits. How many sig figs are there? Don't say a bunch. You have to tell me a number. 9. So there's 4 or 5. Okay, so there's 9 sig figs here. I want you to round it to 1 sig fig. So you have to use this magical tool of scientific notation to dumb it down to 1 sig fig. But the value still has to be in the 50,000s. Okay? So the way you do it is you must determine how many sig figs you round to. I'm telling you 1. Then you start from the left. So you always are going to start from the left on the rounding ones. Doesn't matter if the decimal is present or absent. You always start from the left. And you look at the first digit, that's a non-zero. And it's a 5, right? That is the only number, like true number, you can record. Okay, 5. And the rest of this stuff has to be represented as scientific notation. So what am I going to multiply the 5 by to make it a 50,000 something number? So basically, I want you to take me from the 5 to the decimal. So I'm saying times 10 to the what? 4. Because there's 1, 2, 3, 4 digits over to the decimal. And so if I look at this and I had to tell somebody what that number was, this is approximately, or whenever you expand it back out, this is 50,000, right? 50,000 is the rounded version of this guy. Do you see it? 50,000 is the rounded version of 50,600. Now, if I told you to round it, you guys might say, I'm going to round it to 51,000 because that 6 makes it that number go up. But that's a 2 sig fig rounding measurement. That's going to be our next one. But like if you looked at that, you're like, yeah, it rounds up to 51,000. Just because when you round, you just generally don't care about sig figs. You just round to round. But now we're going to start looking at sig figs as well. So next one, I need 2 sig figs. So I need the first 2 digits to be recorded down here. Okay, so I'm going to put 50 there just for now. But then I look at the next one, and now I need to look and say, you know, the rest of this has to be recorded as scientific notation, but that 6 there, it actually does influence that 0. It influences it to be rounded up. So I cannot write 50. I must round the 0 like I'm supposed to 1, which would be 51. And so then if I'm saying the rest of this has to be represented as scientific notation, you're like, hey, let's just do times 10 to the what? Say again? If I have 51 after times by 10 to the third, because there's 3 decimals after, or to the decimal place, but I know I can't write 51 in scientific notation. I have to write 5.1, right? So that would be 5.1 times 10 to the 4. So I'm manipulating the way I write a number. The number is still the same. It's like 50,000, 51,000. The number just looks different the way I'm writing it because I'm telling you I have to limit to certain sig figs. All right, let's do the next one. 3 sig figs. What numbers do I need to write? 506. So the first 3 numbers here. And then what do? So I'm hearing this, but let's look real fast. Does the 0 influence the 6? No, so we're good here. So times 10 to the second is the way it looks right now, but we know we have to change this to what? To the 4th again. And you'll notice these 4, 4, 4, they keep repeating because the number itself isn't changing. The number is still 50,000 something. And so the scale, which is indicative of the exponent, must stay the same because it's the same dang number. We're just making it look different as we write it in different forms. Let's do one more. Let's do the 6th one. So I need 6 sig figs recorded. Whenever you're ready. So what are the first 6 numbers you want to record?
5, 0.
So I'm not going to put a point just right here. I know it's up there though, okay? I'm going to put a 0 here for now, but that last 0, which is this one, is it influenced by the next one? Yes, so that 6 is saying, hey, 0, you're going up to 1. So that's no longer a 0. I'm actually going to round right here to a 1. And then you'll notice that I'm actually past the decimal. So I'm going to kind of refresh my memory how big this number is. It's pretty big. I'm going to put the decimal where here, and then times 10 to the what here. So where do I put my decimal here? After the 5, and then what do I put here? Times 10 to the 4th. Again, because it's going to be 4 zeros over to represent 50,000. So some of it's going to be logic later on because these numbers are getting very long-winded, but the scale is still the same as the 50,000 number. So we'll keep working on that one. That's one on that you'll be practicing a bit more on your PS. Okay. Okay, so now our final kind of deal here is calculating with sig figs. And that is mainly using the logic of counting sig figs with just addition, subtraction, multiplication, division. Do you see this on your paper? Okay, so read through yours or read through mine. Tell me what are the main differences between these types of manipulations of numbers in terms of sig figs, not like the actual multiplication. What's the main difference, Abby? Or what do you notice is the main difference between the two? It might be different than what I see.
The least number of sig.
Right, so the least number of sig figs is really what we're honing in on in multiplication and division. And then the least number of decimals is what we're concerned about when we're adding and subtracting. So we have cross country or swimmers, yes? Medleys, individual medley or group medley? How did you call it? Thank you. All right, so I'll be honest, I was probably the weakest link of my swim team, but we only had like 4 girls, so I had to swim everything, including the butterfly. Have you done this right? It's not pretty. Okay, it's not pretty. And just think about flopping in the water like that. But I was the weakest. I was the only person that knew how to do it, so I had to do it. But I probably slowed down our times. That's all right. You know, I still got my full ride to college, even though I didn't swim very well. But there's always that person that's going to slow down the team, and it's okay. I was a proud owner of that title. So on a cross country team, you're running, right? Or no, track. When you pass the baton, okay? Pass the baton. I was probably the slowest person doing that too. So I was the weakest link. So I would slow down our time. Just like in sports, in chemistry, there can be the weakest measurement, and that's going to be the one with the least number of the least accuracy, the one with the least number of sig figs. So that's what we're concerned about this. And it's not because we need. I'm trying to find out, every way possible to use sig figs. I'm trying to make us be truthful about our measurements and about our calculations. So when we're thinking of it this way, you're looking for the weakest measurement in terms of sig figs, and in this way, you're looking for the weakest measurement in terms of decimal places. And that controls our final answer, sig figs, or decimals. Not really the number, it just controls how we write it. So, I know this is probably old. I know all the words all about that base, but can't remember sig fig rules. Okay, so let's try these. This is on your sheet. Yes, great. So you guys go ahead, do this mathematical calculation. Just straight up do it, and then we'll talk about sig figs. Calculator. All right, now you can divide very quickly. What's that answer? I hear rumbles. What's the year? 0.8 what? 0.872 what? 04. Okay, I'm gonna stop there for now, just because I have a lot of digits up here. Here's the spot where in your mind you say I'm either doing multiplication and division or I'm doing adding and subtraction. Well, right now we're definitely dividing. So are we concerned about sig figs or are we concerned about decimals here? Sig figs, because that's what the rules say. When you're doing multiplication and division, you are concerned about the least number of sig figs. So looking at our 2 numbers we used, how many sig figs are in the very first number here? Say again, 5. And so your process was, what did you notice? Decimals present, you started from the Pacific, and you counted 5 this way, right? So that has 5 sig figs. This one, again, decimals present, start from the Pacific, dun dun dun, 3 spaces over. So that one has 3 sig figs. Here's our weakest link. 3 sig figs. So this has to be rounded. Do you see where the rounding is coming in now? That has to be rounded to 3 sig figs. So what do I do for rounding? Start from the left or the right. Left, and you record the first 3 numbers because we need 3 sig figs here. So 0.872. And then your job is to say, does that 0 influence that too? Nope. So I'm truncating it there. It's done. What have I not written yet that I need to write? Your units, right? Grams per milliliter. So this answer, to the best accuracy we can give it, is 0.872 grams per milliliter. So within the calculation, we counted sig figs. We wrote out a long number. We knew that was too accurate. Like, nobody's got 5, 6. Well, actually, that person. Nobody's got that many numbers. We need to say this person, whoever measured the volume here, is the weakest link, and that's going to control how we write our final answer. Does that give you some more context of why the heck we're learning sig figs? Someone's like, yeah, sure, lady. All right. So let's do B, okay? Go ahead and do B. Calculate it for me first. Shout out the calculation when you get it. 4,900. Okay. How many sig figs here? Is there a decimal present or absent? Absent. So you start from the Atlantic. And where do you start on the Atlantic? The 4. The 0 is a placeholder. There's no decimal, so you skip the 4. So there's only 2 sig figs there. This one? 2 sig figs. So now that you're looking at them, you just really can tell sig figs very quickly. So 2 sig figs, great. How many sig figs do I have recorded right here? 2. That's the only one that works out, okay? The rest of them you do have to round. Now, if I put a decimal there, how many sig figs would be there? 4, because I'd start from the Pacific and go 1, 2, 3, 4. But the way I had written it previously was saying these are placeholders, these are the 2 sig figs, and then what would the unit be? Centimeters squared, right? Centimeters times centimeters is centimeters squared. All right. All right, so that was counting sig figs. Let's go to C. Add these babies up. 42.78. Okay. Now that I'm adding, what do you flip your brain to? Right, looking for the weakest number of decimals. So the least number of decimals. How many decimals in the first one? 1. This one. 2. This one. 1. So I'm not counting sig figs. I'm simply counting spaces after the decimal place. What's the weakest decimal? 1 decimal. So I'm just looking for how many decimals I need to write here. So I need to round this to 1 decimal point. So that's 42 point what? 0.8, because the 78 rounds up to 8. And that's it. So I just put the 8, and then I need to record this with a unit. What unit do I record? Just centimeters, right, because it's added. All right, keep going. Let's do, actually, you guys do a couple more. Take less than 5 minutes, do some more. I think that's what we work through. Talk to each other, and I'll be around. I like that you guys are adding a little extra notes of sig figs and decimals, and that'll be helpful later on. just need you to believe in yourself, have confidence that you're getting them right, so that you can see that you're good to move on. There's one last topic we're going to talk about. And during this last little minute here, get up and stretch. Go see somebody to ask them what they did on these awesome snow days. Go get some water. We have just one last topic. We have a little extra time here, so try to give you a break. How you get what? Well, this is 25. Sorry, this one on mine, I just looked at that. Mine has a 5.0. This is 250. That times 2, that's 100. I think I sometimes make copies of mine. Mark that. Did you get 100 or 1.0 times 10 to the second? 1, 2, 1, 2, yes. And then I just need to fix mine. My copy. Sorry about that. Gee, guys, my copy is just slightly different. This probably what you got was 100. And then you can't write it as 100 because you need to indicate 2 sig figs, and that only indicates 1 sig fig, so then I changed it to scientific notation for you to help with the sig fig cause here. So, all right, stretch break. What you gotta do? Yeah, go quickly. Just sign out on the door when you go out. Oh, and these cards, I was going to do in class, forgot. These, write your name on it and give me some sort of drawing to indicate something cool about you, special about you. I'm going to use these as flashcards so I can remember your name. I'm really sorry, I'm working on it still. So, write your name, draw something about you, makes you special. And that's a very biased question, it can be anything. All right, artists, let's jump back in. Our last main topic is density. And you already know a little bit about it, so I don't think this will be new. It won't take very long. But I just want to show you how to manipulate the equation of density a couple different ways. This first part, you write down what you need to. I think we all know, maybe we don't. I might be making an assumption. Density of water is 1 gram is equal to 1 milliliter. So we write density of water as 1 gram per milliliter. This is something that you need to know. Water is kind of our standard, and we compare everything to water. Just so you know, it's everywhere in our world. It's easy to compare something that's everywhere. And this is something that's obviously very relevant to engineering practices because they have to be cognizant of what water is, because a lot of times we have things interact with water. So if we want something to sink in water, it has to be relatively blank dense. So if water has a density of 1 gram per milliliter, and we want something to sink in water, does it need to be more dense or less dense?
More dense.
More dense, more compact. It's going to have more mass than the space it takes up, so it's going to therefore sink. So anything with more than 1 gram per milliliter will sink in water. So that might be common knowledge, but now you're just going to be relating them to more mathematical descriptions as well. So anything that we want to float on water, we want its density to be what? Less dense than water, right? So we want it to float, then we need its density to be less. So we're going to be exploring density more tomorrow. And you guys are going to get 8 random objects, and you're going to have to find the density of them and then place them on a graph in relation to water to figure if they're going to float or sink. And then talk about like the material side of it, like what could this be used in? Like something less dense than water, what might we use it to build? Something like that, okay? So if you're looking at these 3 densities of corn syrup, vegetable oil, and water, which one's going to float on water? The vegetable oil, right? This one's going to stay high, and then water's going to be in the middle, and then this corn syrup, which is more dense, you can say it's 1.1, is going to be down low. They're not going to be floating, they're going to be hanging out like this, right? And that's how this magical lava lamp works. Here we go. So what's this yellowy stuff? Vegetable oil. What's this blue stuff?
Corn syrup.
So the blue stuff has food coloring in it. It was once clear. It's just water, right? So you can see the water's on the bottom. There's food coloring and glitter in there, and this is all oil. So we make these great lava lamps. We make these great elementary schoolers. It's soothing. It's like therapy. Okay, you can pass it around. All right, so that's one thing we're going to be, we're going to talk about the uses of density, and you can go home and make yourself a nice lava lamp. There's no energy needed either. It's just mechanical energy. All right, so let's talk about the basic calculations of density, and then I'll have you guys start on the 1 through 5 on your desk, and hopefully you'll get that done in class so you won't have to do it at home, okay? So our very first example, this is like a geometry-based question, okay? We have a mass given, we have a length and width given, and a height. What is the formula of density for a rectangular solid? So I'm going to expose you to big, huge, narratives about a problem. But I want you to ignore all the crap and just look at the information that's really important to our question. What is our direct question here? What are we looking for this question up here? Looking for density. Okay, stop there. We're looking for density. Density, I'm showing you how to approach a problem, okay? Density is whatever what? Mass divided by volume. So our secondary questions are, what are the mass and what's the volume? And then we're just going to divide them, right? So do we know the mass here? Yes, we know the mass. We know the mass is up here, 152.2 grams. Do we know the volume? We have a way to find volume, right? So I'm going to kind of put that over here to the side. Volume is equal to, tell me your process of finding volume. Okay, so length times width times height, which are what numbers here? 3 times 3 times 2 centimeters. Sorry, centimeters. Okay. 3 times 3 is 9 times 2, 18. So what is the volume? Perfect, 18 centimeters cubed. So now do we know volume? Yes. I'm now going to take my mass given, divided by the volume I calculated, all by myself here with you guys. And before we move on, I'm actually going to talk about sig figs and then we'll actually divide. According to my math here, what should I be looking at in terms of sig figs or decimals? Which one? I should be looking at sig figs. What should my volume then be recorded as? Not 18, right? You'll notice I have 1 sig fig in all of these. What should I record this to? If I put 1.8, how many sig figs is that? 2. So I have to round this up to 20. No decimal, right? I have to round this to 20 centimeters. Now that's called rounding in the middle of the problem, and that's usually a no-no, because if I round here, and then round there, and then round the end, I'm going to have rounding error, because I have rounded 3 times within one problem, so I'm skewing the answer, right? So that's why I didn't do it here. But I want you to just be aware that this should be recorded to 1 sig fig due to our specific great ruler of 3 centimeters and 2 centimeters, right? It should be recorded 1 sig fig. So we're going to keep that in mind later on at the very end. Okay, so I sometimes will put this here and just put a star next to it so I remember. But I'm not going to record it like this because that's going to cause rounding error. That's what I actually did write 18 here. So now, when we're dividing, what are we considering? Sig figs or decimals? Sig figs. Who should be our weakest link? The 18 one, which we know is only supposed to be how many sig figs? It's supposed to be 1. So at the end, so I usually, I'm like, I'm going to go ahead and write this down. I need 1 sig fig at the very end. So let's see what our middle, our answer that we get before we round is. So what's this number divided by 18? 8 point what? 45, I heard. 5. Okay, repeat again. Grams per centimeter cubed, right? So that's kind of our initial answer. But from there, we need to round. So what would you round it to? If we only need 1 sig fig, as we kind of previously determined. What would you round it to? Does this 8 get affected by that 4? No. So what happens? Nothing. It's 8. Okay. 8 grams per centimeter cubed. I can't go 9 because that's me rounding there and then there. I can't round twice on the same number. Okay. So that was just a density problem, but now we know sig figs, so we just have to be aware of them as we're going through the process. All right, next. We have a mass. Oh, we have a rock. All right, so a rock doesn't have a nice little, like times with some height kind of deal. The volume of the rock is calculated by water displacement, which means just drop a rock in a graduated cylinder with water in it, and the water rises. So it's just called water displacement or volume displacement. The original volume of the graduated cylinder was 60 milliliters. After putting the rock in it, the water level rose to 75 milliliters. What's the density? Okay, so again, if I ask for density, what am I actually asking for? Say again? Mass divided by volume. What is the mass of our rock? 45 grams. How many sig figs there? 2 sig figs. Okay, so I'm just going to put 2 and just remember. What's my volume? How do you know? Okay, good. So the rock is the volume we're looking for, not the water. We're looking for the difference of the water before and after the rock was placed in it, and that's how you find the volume of an irregular object, meaning that it doesn't have a specific way to calculate its volume by geometry calculations. So we're going to take this and divide it by 15 milliliters to get 45 over 15 is 3, right? 3 grams per milliliter? Thank you. Okay, so you should always, at the very end, just take a breath and reflect on the sig figs. So we have 2 sig figs, 2 sig figs. This needs 2 sig figs. How do I make it 2? 0.0. Okay, and that is our alternate way of representing density as grams per milliliter. Okay, you guys have about 15 minutes. There are 5 problems on the density sheet in front of you. I want you guys to attempt. One of them is pretty interesting. The other ones are not bad. You can work on them with anybody you want to. If you move to a lab, you just have 15 minutes. Oh yeah, I'll come and pick up your cards so I can memorize your questions. Thank you for waiting. It's 8.